We continue with our topic on differential equations, and we will now look at what a solution is. So let's say we have a differential equation, dy dx is equal to y, or y prime is equal to y, which is the same differential equation, just a different notation. What does it mean for us to have a solution? Well, let's first return to some other equation, x squared is equal to 4. Now, if we want to know if we have a solution, let's say x is equal to 2, what we do is we put this value into the equation and see indeed that 2 squared is equal to 4. So a solution here is a number that satisfies this equation. Now, if we look at the differential equation, a solution is a function, our unknown function, the dependent variable, y of x, that satisfies the differential equation. So if we plug our solution into our differential equation, the left-hand side should be equal to the right-hand side. Now, let's look at the function y of x is e to the power of x. If we look at its derivative, we see that the derivative of e to the power of x is e to the power of x, and indeed for this function it is a solution because the derivative is equal to the function itself. Well, let's have a look at yx is equal to 2 e to the power of x. The derivative of this function is equal to 2 e to the power of x. So 2 e to the power of x is also a solution. Now look at some kind of constant times e to the power of x. Doesn't matter what the constant is, it's just a number. We know that the derivative is equal to c times e to the power of x. So the function and its derivative are equal to each other, and this is a solution as well. And this is a solution for every value of c. So we don't get just one or two solutions, we get infinitely many solutions. And in fact, we get a family of functions that will solve a differential equation, and usually they're parameterized with this or some kind of coefficient. So we don't talk about the solution, we talk about the general solution of a differential equation. And for this particular differential equation, y prime is equal to y, the general solution y of x is equal to c e to the power of x, with c some kind of constant. So we don't just get one solution, we get a whole family of solutions. For every constant, a value of the constant c, we get a different solution. This is because our problem is formulated in a very general way. Now, let's look at the concept of an initial value problem. And what the initial value problem is it's a combination of a differential equation. Let's say y prime equals y, but we also have a starting value, that y at point 0 is equal to, for example, 1. Let's plug this in, because we know the general solution is y of x is equal to c e to the power of x. And this solution, this general solution, is the solution to this differential equation. But now we have more information. We also have the condition that y at 0 is equal to 1. So we plug that in, and we get y0 is c e to the power of 0, and e to the power of 0 is equal to 1. y0 should be equal to 1, which means that c is equal to 0. So our particular solution of this initial value problem, so the combination of a differential equation and some condition, some usually initial condition, is equal to y x is 1 times e to the power of x. So where do we see these initial value conditions? Well, we had we saw that we had a problem before where we dropped an object and we saw that the model yielded dv dt k dv, what was it again? No, sorry. M times dv dt is equal to m times g minus k times v. That was it. So this was our differential equation. But it didn't say with what velocity we let the ball go. We could let it have an initial condition where the initial velocity would be equal to 0 meters per second, but we could also start with 10 meters per second. And these initial conditions do not change the differential equation, but they will change the particular solution of our problem. So instead of having a solution where from 0 it slowly ramps up to some stable condition where we have v and t, it could start at a different value and have a different final solution. Something like this. This is not necessarily the solution to this, but you see that there are different solutions depending on the initial value. And what we see here is that, and I believe actually this might just go to the same value. If we look at this problem, the solution we found was e to the power of x, which goes like that. And it crosses the y-axis at 1. Now, if we have different values of c, what we'll see is that we'll just get different values. If c is 0, we get a very boring solution. So for every initial value, we'll have a different solution for negative values of c and for positive values of c. And for the same problem we have here, for different values of the initial condition, we'll have a different trajectory, a different velocity. The model stays the same, but the solution to the problem with that particular initial value changes. And so this is called an initial value problem, and it highlights the fact that the general solution provides a family of solutions, but if we want one particular case, for this example where the initial velocity is equal to 0, we find that we get one particular solution. So that's the difference between the general solution, which we get when we only look at the differential equation, and a particular solution when we also have initial values.